did it at first. See how I erased all of them? Thank God I fixed that. Yeah, that one's like really easy. Jeez, I did like 3 times.
I was confused.
So why are you fucking saying this is one bigger, so just.
Do.
What are you responsible for 7 years of track? That's like fun.
You got this question.
So then apparently you got so these what do you do here?
Live right now.
Oh, I didn't know we got different questions.
For X itself, not the fact. Oh yeah.
I'm so glad we got this exam done though, bro. Now this is vacation.
That's no, but I got one.
I don't got
I got one completely off.
Ah.
After that, yeah.
Hello. Why is that not recording? No. I think I'm gonna shut this one off. Hope that's better. I don't know. Why is that not recording?
I got a 63. You?
All right, good. All right. Anyone not get their exam yet? Lando.
Really tonight. Oh, tonight.
Boom.
Oh yeah.
Castle over there you go. Everyone else got it, right? All right. Spring break is a looming.
Oh my god. I got the whole last one.
Now I'm nervous.
My brain kind of just blanked out when I got to that one, honestly, but I got the whole thing right. Yeah, I saw like an 81.
Now I'm nervous. All right. Everyone's got their exam back. I will stay after class to go over any questions you want on it. Just a reminder, we do have a final exam, which is cumulative, which will pull out the biggest things from exam 1, exam 2, which is now history. So it's definitely worth your time to look at what you got wrong, understand why you got it wrong, and don't get it wrong again. What's up?
Do you think for the final exam we should say only our exam notes or
the exam questions will definitely be the ones that make their way back. Cool. tonight's going to dive right into it. And then we have spring break. I know the question was last time, do we have homework? And unfortunately, yes. But I'll set it due for 2 weeks from today. So if you're literally taking a break, I think that is appropriate. But I'll keep it open for those who want to, use their time their way. So, and then we'll definitely be back on track afterwards. And I think the next exam is at the end of this month. So not that we want to really hear that, but just to kind of keep that all in perspective. So we have a week off, and I think we have like a full week, and then I think another full week, and then exam 3 after that. All right, so we are going to talk about rational functions this evening. Bottom line up front, we're going to look at basically quotients. We looked at that in unit 1. So we looked at don't divide by 0. So we're going to continue to focus on not dividing by 0. But specifically, if you have a polynomial over a polynomial, we're going to call that a rational function, and not just say, all right, these are the excluded values, but what takes place graphically. So we'll talk about things called vertical asymptotes. We've already seen them. We will see holes in a graph. We've seen them in unit 1, but we will actually build them here. Another common thing that we're going to be able to do at the end of the section is, given a rational function, state all of its asymptotes. So in addition to vertical, there will be horizontal and oblique asymptotes, which requires division. So we can use synthetic or long division. So that comes back into play tonight. We're going to look at more end behavior for these types of functions and behavior near the vertical asymptotes. And that's really it. I say that it's really it, but it's quite procedural. There's not a lot of problem solving. Like, there's basically no problem solving. It's like you do this and that's it. So that's kind of nice for students. Know this, do this, that's it. That's what I mean by procedural. But there's still a little bit to take away here. Then we end really quickly with solving polynomial and rational inequalities. And that's it. That's our polynomial and rational unit. I wanted to get this in for exam 2. It didn't. It's all good. When we come back from spring break, I'm going to tweak what I have originally planned, and I want to get into trigonometry. So I was going to go into exponentials and logarithms, but more importantly for calculus 1 anyways, is that you have a strong foundation in trig. So I'm making an adjustment, and then we'll end our course with exponentials and logs, which play more of a role in Calc 2. But so that you're ready for Calc 1 100%, I definitely want to review the trig big stuff. All right, so with no further ado, we previously saw this function, x to the negative 1, in our power functions. So just kind of quickly reminding us, a negative 1 exponent is a reciprocal, which I did there. And the way I kind of think about it, I try to memorize less. This is x to the positive 1. And so if I want to graph x to the negative 1, either I know it by heart, or I know that a negative exponent is a reciprocal. And so when I focus on the 0 right here, its reciprocal is going to create what we call a vertical asymptote. And its equation is x equals 0. Next way I kind of bring this to life, this is a small output, meaning it's just above the x-axis there. So that's a small output. It's a small y coordinate. So if you reciprocate it, if y is the reciprocal, then something small reciprocates to big. And similar argument, this is a big output on y equals x, so its reciprocal is small. However, we've had this discussion, just have it one more time. If you take a really big output like a googol, that is a number. It's 100 with 100 zeros after it, so that's a huge number. And you reciprocate it, you get 1 over a googol. Technically, it's microscopically small, probably smaller than anything in the universe. But it is something. It's above 0. And so we get closer and closer and closer to 0 as we get bigger and bigger reciprocals. And so you get this graph right here of the reciprocal of y equals x, at least in quadrant 1. And we're going to call that a branch. That is a branch of this function. We have a similar branch down here in quadrant 3. And furthermore, looking at this graph, we now have a horizontal asymptote at y equals 0. So to give asymptotes a little more depth, it is a line that the graph approaches as you take really large x values or really large negative x values. So it gets closer and closer to this horizontal line of 0, but it does not intersect it in the long run. So again, if you take a googol, which is a huge number, and reciprocate it, it's microscopically small, but it's still above 0. Now, if we took like a googol squared, oh my God, my brain can't even fathom that. But that's even microscopically smaller than the googol. So it's getting closer and closer to becoming 0, but it never gets there. It never intersects it. So that's what a horizontal asymptote is. A vertical asymptote is literally the same idea. As we take y values further and further away, so really large y values and really small or really negatively large y values, these y coordinates are actually getting closer to that vertical line, x equals 0. So we call that a vertical asymptote. I say that because I don't remember if I said this, but there is like a question. It's not a trick question. It says, does a graph ever intersect its asymptote? The answer is yes. Not always, but it absolutely could. So to emphasize, in the long run, I'm going to draw a graph that won't approach that. So in the long run, it's going to be trapped by here. It's going to start getting closer and closer and closer, closer and closer to that. But before that, so again, going back to what truly is an asymptote for large x values, it's going to get close to it. Well, now it's from here on out, it's going to get closer. But prior to that, it intersected it many, many times. And there's applications of that inside of calculus. So it's not a big deal. If the average person who's in academic math will probably say it never intersects their asymptote. And that's just not true. It's not a big deal, but now you know a little bit more than the average person. All right, so far, back to life. We saw that 1 over x is a power function. We're going to specifically call that one right there the reciprocal function, since it reciprocates. And what I drew here in blue is the graph of 1 over x. In case that got muddied. The takeaway so far, we're going to work this graph. Okay. And there's 2 asymptotes. X equals 0, vertical, y equals 0, horizontal. Common theme in this course is to apply transformations to a parent graph. So I'm going to call it the graphing form is a times x minus h plus k. So we should be familiar with h, k, and a. Basically, h is going to shift that entire set of points horizontally. K will shift that entire set of points vertically. And a will stretch that. What does that mean for us? our center of the transformation, as it's called, is HK. When we worked with parabolas that shifted, the vertex was HK. What I'm trying to say here is that our HK is going to be where the two asymptotes intersect. This right here, called the origin, is really going to be our shifts. Because if I shift this blue graph left or right, but I'll just say to the right, guess what's also shifting? That vertical asymptote. So this vertical asymptote, wherever we shift, will become our new H value, or our H value will become the new vertical asymptote. Similarly, if we shift it up or down, this horizontal asymptote will become our K value. A will just make those branches wider, narrower, and it's not really a big deal. I'll show you how we're going to deal with that in a minute. The goal so far is to know HK will be the intersection of our two asymptotes. Therefore, the equation of the vertical asymptote will be x equals h, and the horizontal asymptote will be y equals k. So let's just put it in motion. To graph a rational function, and we're going to do sketch graphs in our notes. We're going to identify the center, and then we're going to mark in the asymptotes. To get an idea of what the curve is doing, just do some point plotting. Literally plug in some quick numbers, get an idea, like 1 or 2 or 3 points. Just remember that there are 2 branches. Sketch your branches so that they approach the asymptotes, and we're done. Let's practice it. F of x equals 2 divided by x plus 3 minus 1. What is my h value? Well, what do we know? What's the horizontal shift going to be? To the left 3 or to the right 3? Here's an easy answer. What makes division by 0 right now? -3. So we can't input -3. So it shifted left 3. Just like we couldn't input 0 up here. You can't put in 0. Vertical asymptote. We can't input -3. There's your shift. You know it's going to be at -3. So quick graph would be like boom, 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 boom. That's another quick way of remembering it. What is the excluded value? This is our K value. Did it shift up or down 1? Down 1. So there's your new center. I shouldn't even put that as a point, but I just want to highlight it for a minute. It's not actually going to be on either branch, but that's what I mean. That's like your new center. That's like the new origin. Remember they intersected over here just a couple of minutes ago? That's our new center. So now we're going to have 2 branches. To get an idea about where the graph looks like, sub in some numbers. So I'm going to sub in the number -2. Subbing in -2 right here. I think I can do this in my head. -2 plus 3 is 1. What's 2 divided by 1? 2. And then 2 minus 1? 1. All right, so if I estimate it, it's like right there. I arguably claim that's all we need. I know it's a branch over there. It's got to get closer to both asymptotes. I have an idea about what the reciprocal function looks like, so get closer that way, branch downwards this way. And if someone asked me for more accuracy, I would just keep plugging in points. That's it. So minimally 1. Someone wants more accuracy, tell me how much accuracy you want. You want 2 points, 10 points? I'm happy with just 1. Remember, there's a second branch, so let's sub in -4. And again, I think I can do that in my head. -4 plus 3, -1. 2 divided by -1. -2, take away one more, -3. So just reminding myself, if this is -1, I have to just be lower than it. Something like this. Approach your asymptote, and we're done. Sketch a graph. That's all I'm looking for. State the equations of the asymptotes. I did that. But I do want to emphasize they must be equations. Saying -3 and -1 is not enough. X equals -3 is a vertical line. Y equals -1 is a horizontal line. State the domain and range. -infinity to -3, union 3 negatively to infinity is our domain. And our range values, we can say, I'll do it in a weird way just for a minute. We have -infinity, to -1, union -1 to infinity. All right, so we actually don't write the range that way, just reminding us it's really the y coordinates, but you can see it that way. And state the end behavior. End behavior means as x gets negatively large. It also means as x gets positively large. This arrow is not falling. It is rising. It is getting closer because that's what an asymptote is. So that means rising if you're getting closer, but it is trapped. There's like a ceiling here. It's trapped by that asymptote. So we would say as x gets negatively large, the outputs want to be -1. They want to become -1. They're not rising to infinity. They're rising to try to become -1. Similarly, on the right, as x gets really, really large, the outputs are falling. Yes, they are falling, but they're not falling endlessly. They're getting closer to -1. And so when we have end behavior that's approaching not infinity or negative infinity, literally that's the definition of a horizontal asymptote. Not that we need to know that, but that would be the definition of a horizontal asymptote. It's not rising forever. It's not falling forever. It could be rising towards a number or falling towards a number. That means you have an asymptote, a horizontal asymptote. Anyhow, any questions so far? All right. Part B. I'll just kind of go through it cleanly now over here. Where is my vertical asymptote? Quick hint again, remember we don't want to divide by 0, so x cannot be 2. There's your horizontal asymptote. What is our shift upwards? Yeah, someone just wrote it in weird order, but that's okay. So that should really be like +4 over there. And we know we can add in different orders. So that's just the author making sure you're paying attention. But this is your K value, so up 4. There's your new center. That's acting like the new origin. To get an idea about the graph, choose something near your new center. So choose 3. 1, 1, 4 minus 1 is 3. This is a y value of 4, so something like this. Approach your asymptotes, and you're good. Choose something else. You could choose 1. You could even choose 0. Might be nice to choose 0. Maybe it's not nice to choose 0. Now that I'm relooking at that, 1 over -2. Maybe I'll go back to 1. That's going to become -1. 4 minus -1 becomes 5. So I'm just above this. There's a quick sketch. Good enough for what you need in calculus for when you actually do something with that. I'll just reiterate it for the last time. Someone asked me for better accuracy, I plug in points, but we'll let it go. That's, trust me, good enough. I already got my equations of my asymptotes. The domain is -infinity to 2 union 2 to infinity, and my range would be -infinity to 4 union 4 to infinity. And behavior, as x gets negatively large, so as f of x approaches -infinity, as x approaches -infinity, f of x approaches 2, both sides. All good? Pretty simple? All right. Then, wish there was a way to erase all of this. That's better. Here's a function. Linear on top of linear. Does not look like a reciprocal with h, k, and a. Do we agree? Doesn't look like what we just had there. This was a number on top of something linear, and that was our k value. This was a number on top of something linear. That was our k value. Example C is not a number on top of a linear. Do we agree? Right. But I'm asking you to write this function in quotient plus remainder over divisor using division. So can we use long division? Sure. Can we use synthetic division? Sure. Which one do you want to do? Synthetic. 4. 2, -5. Bring down the 2, multiply, add. 3 is the remainder. If that's the remainder, this is called a constant. So the quotient is 2 plus remainder 3 over what we divided by. And that's why the author switched the order for you. Because when you have a linear on top of a linear, you really do have a transformation of the reciprocal function. And that's how we could graph that. That's how we can gain all the information about that. So just recognize you can't input 4 here. You still can't input 4 here. So you know the vertical asymptote is at 4. Here's something to notice. The shift upwards is 2. I'll come back to this in about, 15 minutes. Look at this ratio. It's 2 to 1. Is that a coincidence? We'll see. No, but the ratio here is 2 to 1, which is 2, ends up being our horizontal asymptote. Gotta use a little more caution on that later, though.
Excuse me.
What's up?
The 2 here, is it possible to reverse it, where we say 3x over 4?
Yeah, because addition can be written in any order. If this makes you happier, you can absolutely put it that way. Is that your question? Yep. So our new center would be 4, 2. I won't drag us through all the stuff there. Just want to emphasize you can take linear over linear using division and get it into the graphing. Oh, now that's coming up. I don't want to hear my voice over there. The whole thing's gone now. Great. Just let me get you your test before you leave, even if you have to interrupt me for a minute. Just kind of like wave me down 5 minutes before. All right, let's work backwards on this. Given a graph, write its equation. So where do you think we should begin with this? Yeah, so identify the asymptotes, because if we can find where they intersect, that's our center. We have our H and K. How do you identify your asymptotes? There's nothing elegant here except looking at it. All right, so in my opinion, this is getting closer here. If I go down, yeah, it crossed here. So my best faith would say this line right here. Since this is the y-axis, this is x equals -2. Similarly, I believe it's not going to cross this. We have evidence on both sides that that must be our horizontal asymptote. So given this information, that's 1, 2, 3 downwards. So I know at least this. I give it a quick little check. I don't want to input -2, so that has to be a +2. Just need to know that I'm shifting this down 3. That's the power of knowing transformations. What I don't know is this multiplier on top. But I do know if I choose a number near the center, like -1, what has to be the output? 0. So much like an algebra course, or anytime you want to find an A value, you kind of identify your transformations or whatever key features you can from the graph, and then choose a point on the graph. I like that one, but you could choose that one or whatever you like. I just happen to choose the x-intercept right there. When x is 0, oops, it's not true. When x is -1, y has to be 0. So we get 0 equals a over 1 minus 3. A divided by 1 is just a. Add 3 to both sides. And you find that your a value has to be 3. So a nice clean answer would be f of x equals 3 on top of x plus 2 minus 3. What appears to be our vertical asymptote? 1. X equals 1. What appears to be our horizontal asymptotes? 1, 2. I know where he's sitting. It could be arguably just a little tough to count. So that's 1, that's 2, that's 3, 4. Yeah, y equals 4. Anyone see a point that we can use? X equals 2. Here's x equals 1. Here's x equals 2. And y equals 2. 2 comma 2. Sub in 2. See, working near the asymptote usually leads to some pretty nice values. All good. We're going to have a plus 4 equals 2. Subtracting the 4 makes a -2. And I kind of expect all those things. So before I move on, putting transformations with a reciprocal graph. Started tonight with 1 over x as a branch in quadrant 1, a branch in quadrant 3, and the asymptotes intersected at 0, 0. Take the center where the asymptotes intersect, shift it 1 to the right and up 4. Boom. And then A values can be tricky, right? We know from earlier, they stretch, shrink, make graphs do different things. And they also can be negative, which makes, again, a branch in quadrant 1, if it was reflected, would be in quadrant 2, and a branch in quadrant 3 reflected would be in quadrant 2. We're kind of seeing that shape right there. So the fact that I'm getting a negative and seeing this curvature, I'm feeling pretty confident in my answer, right? Always a good time to review transformations. So we just looked at the case of a number on top of a linear on top of a linear with after division led to a number on top of it. But in general, a rational function is the quotient of 2 polynomials. So to remember us, we looked at power functions, but polynomial functions are only when you have positive exponents that are not fractions or decimals, so positive whole numbers. So basically, if you have a linear on top of a linear polynomial, a quadratic on top of a quadratic, or a cubic on top of a quadratic, or a quadratic on top of a linear, all those, any case, that's what we call a rational function. If you see a sine function when we get to trig on top of a quadratic, we'll call it a quotient, but it's not going to have any of these properties. But when you take a polynomial on top of polynomial, we're going to get a lot of characteristics.
So as of now, there's no restriction on it.
The restriction is they both have to be polynomials.
Okay. Thank you.
So I want you to look at these two functions. And are they the same?
Yes.
Why do you say yes?
Because the 5 on the left hand side, or g of x, you can eliminate the x minus 5, and you're going to have x plus 3 and x minus 2 on the left side.
Mm-hmm. Who agrees? We can cross out the x plus the groups of x minus 5. Cancel them out. And if we cancel them out, it would be exactly f, right? So yes, and 100% no. Are they the same function? There's either a yes or a no, and the answer is no.
Goodness.
They are not. So give me a number. Give me an x number. A number for x. 2? That doesn't take 2.
Yeah, never mind.
And that doesn't take 2. So far we have evidence that they're the same. Neither one of them likes 2. Okay, you want to use 3?
Or you know what, 10 would make more sense.
10 makes more sense. You get 13. You get 8. This is 13 over 8. This is 13 times 5 over 8 times 5. Can we cross out 5 over 5? Yep. So you get 13 over 8. Okay, so it's working. You want to try 5? You get 8 over 3. That's a number. 8 divided by 3. You get 8 over 3, and you get 0 over 0. And you might not know, but you're not allowed to cross out 0 over 0. You can't have 0 in the denominator at all. Funky things happen. Not allowed. So except for 5, these are exactly the same. They're going to make the same numbers except at 5. 5 is the only issue. And 2 is an issue for both. Neither one of them like 2. So it's the 5. Something interesting is happening at 5. because we know what's happening at 2. What's happening on the graph here?
Is that an asymptote?
It's at an asymptote. What kind of asymptote?
Vertical?
Vertical. If these are behaving the same way, except for at 5, my gut feeling says we're going to see a vertical asymptote at 2. And I'll tell you the spoiler, we will. But at 5, let's come back to that. For both functions, x can't be 2. If we consider x values extremely close to 2, what's an x value extremely close to 2? All right, well, 2, here's 0, 1, 2. We can come from the left. So what would be a number really close to 2 if we came in from 0, then 1, then 1.9? 9? How close do you want to be? I don't know. I could have went 1.9. Let's 1.99. That's pretty close. What's this? 4.99. What's this? Negative 0.01. And if you multiply top and bottom by 100 there, you get a really big negative number. Do you see it? Let me talk it up. So let's actually see it. Sub in 1.99. F of x would be 4.99 over negative 0.01. And a quick way to think about that without a calculator is multiply by 100. This becomes negative 1. And the top becomes 499. You get a big negative number. What if we did choose 1.99? Then this would be negative 0.001. And we would multiply by 1,000, which would make this ultimate value even bigger negative. And so that sounds like a decrease. That sounds like the graph is falling there. Same thing's going to happen right here. And these numbers, since it's not 5, are going to cancel out. So they're both going to do the same thing. And when we choose a number on the right, so we're at 4, we're at 3, we're at 2.5, we're at 2.1, we're at 2.01, or maybe 2.001. This value becomes 5.001. The denominator becomes 0.001. With me for f? We'd multiply top and bottom by 10, 100, 1,000. The top is getting positively big. The closer we get to 2, the bigger the number we're going to have to multiply top and bottom by, which means the output's going to get bigger. We now know what's happening on both sides. From the left, for both f and g, they're both decreasing. And from the right, they're both increasing. That is the evidence we need to kind of prove that there's an asymptote at 2. We can be close, but it's getting further and further and further and further away from the y-axis. So it's just decreasing forever. That's what I said a vertical asymptote is. You're getting really close, but the y values are getting further and further and further away. The closer you get, the further away they're going. But what about at 5? That's not answered here yet. So if we tried a number like, I don't know, 4.9, this would be 7.9 over 2.9. This would be 7.9 over 2.9, and that would cancel out. I don't even care. They would be just a value. If we tried 4.999999999, this would be a number like 7.99999 over 2.99999, and this would be the same thing. I'm literally like about to plug in 5. 4.9999999999999. This wants to be 7.9999999 over 2.99999. However, this is going to be the same thing. So I'm saying a number 7.999999999 over 2.99999. What does the top really want to be?
8.
What does the bottom want to be?
3.
We're really close to 5. Both of them really want to be 8 over 3. I'm going to plug in 5. I'm literally going to plug in 5. You get 8 over 3. What happens when I plug in 5 here? We don't know. But what do we think it's getting close to? 8 over 3. We don't have an asymptote. We have what is called a hole in the graph. At 5, 8 over 3, that's a filled in dot. It's there. It's a point you could plot. This one, we're not going to draw an asymptote. We're going to plot the point, but we're going to make it an open hole. It's not a vertical asymptote. It's a hole in the graph. I'll come back to that. But if you're following that logic, to me, it makes complete sense. They both want to be the same value. At 5, this guy can handle it. They can't. But you get as close to 5 as you want. They're craving to be 8 over 3. They're almost there. And then when we plug in 5, it does become 8 over 3. But this one doesn't. So we just say, man, you be as close as you want to 5. It's going to be as close as you want to 8, 3. And that's going to translate to a hole in the graph. So this is the must knows. This is the big one. The graph of a rational function, a polynomial over a polynomial, has a vertical asymptote when you make a 0 in the denominator, but not a 0 in the numerator. Meaning, 2 made a 0 here, but not there. 2 made a 0 there, but not here. 2 is going to become a vertical asymptote because the graph is just going to either go up, it's going to rise forever, or fall forever. We'll come back to that. You will have a hole in the graph every time there's a 0 in the denominator, as well as a 0 in the numerator for the same x value. This case, 5 makes a 0 in the denominator, 5 makes a 0 in the numerator. 0 over 0. Hole in the graph. Horizontal asymptotes. 3 cases. Top heavy, bottom heavy, or equal degree. About 15 minutes ago, I said, notice something. This is linear, which we call degree 1. This is linear, which is called degree 1. These are equal degree. The ratio of the coefficients which I highlighted, ended up being the horizontal asymptote. So if this should say, and I didn't write it, equal degrees. If you have a greater degree in the denominator, which I call the bottom heavy, then the horizontal asymptote is going to be 0. So we have case 1, bottom heavy, case 2, equal. And if the top is heavy, why does things just stop working on me? Okay. If you have a top heavy, oh, I got this wrong. Bottom's bigger, top's bigger. There we go. If the top has a greater degree, there is no horizontal asymptote at all. Great. So this is really the biggest thing of the night, and the most important thing that you would need to know for calculus: where your vertical asymptotes are, where there's a hole in the graph, and what's it doing on its ends. So we're just going to crank through some examples, talk about slant asymptotes, and then end with solving some inequality things. Find the holes, find the equations of all asymptotes. So you want to begin by factoring. That doesn't factor. This is a trinomial. Its leading coefficient is 1. 1 multiplies to 12, adds to 7, 3, and 4. Next, what are the zeros in the denominator? Clearly, -3 and -4. What are the zeros of the numerator? -3. Since this is a shared 0, we have a hole at -3. Since this is not a shared 0, we have a vertical asymptote at -4. So we have a hole when x is -3. We'll come back to the y value. We have a vertical asymptote at x equals -4. And we have a horizontal asymptote. This is bottom heavy. It's going to 0. Now, besides the fact of that, why? The bigger question, why? Because I said so. Let's sub in, what does it mean in the long run? Remember, a horizontal asymptote is as you move further and further and further away in either direction. It's like the end behavior. So if we sub in a number, this is 103. If we sub in a number down here, this is 100 squared, already way bigger than 103, plus 700. So now we're destroying that numerator, plus 12 more. But the fact that, like right here, this was already destroying it. Never mind everything else. 103 compared to 100 squared, I think about it as like winning the lottery. That would be my luck. You just won $103 million. Sweet. But so did a lot of people. Damn it. You only get a penny. Everyone won the lottery at the same time. So if you have a number, but you're dividing it by a bigger and bigger and bigger and bigger amount, it gets smaller and smaller and smaller. You know, try a million and three. Okay, that's a pretty big number. But a million squared destroys it. So that's why when you have a greater degree in the denominator, it's going to go to zero. Not just a fact, because we do it by plugging in numbers. Y is 0, horizontal asymptote, x equals -4 is your vertical asymptote. How do I find the value of the y coordinate at the hole? Well, I took the time earlier to be obnoxious and say, let's get really close to 5 and show that this wanted to be 8/3. This wanted to be the same thing because we're not inputting 5. They're going to be the same thing. This can handle 5. It does become 8/3. So if we just didn't pay attention to that issue, we would have got the 8/3. To find the y coordinate of the hole, just pay no attention. Okay, so it's not like I'm not paying attention, but I guess I'm not. Pretend that wasn't there, and we can figure out what its value would be. So if that wasn't there, it would be 1 on top of 1. We would have a hole at -3, 1. Okay. Just don't know why that's not working. All right, why don't you take a moment, see if you can find any asymptotes, any holes, and any horizontal asymptotes. Yeah, it's okay. But it's not okay because I guess you can't see it, right? Oh man, I wanted to pull up Desmos on this. Everyone's got it written down, right? So just for a moment here. All right, so I just went through. We'll look at part B. I'm going to back up to part A for a minute. This was the first question that I worked out. We factored this, or I factored into x plus 3, x plus 4. The zeros were -3, -4. -4 was our vertical asymptote. It makes a 0 in the denominator, but not the numerator. -3 was a 0 in both the numerator and the denominator, and you can see in the hole in the graph. No, you can't. All right, you're not going to see it on a graphing calculator. You're not going to see it on Desmos, although Desmos does have this cool option that if you drag your mouse to the point, it's a little finicky, but get there. It won't go right at 3. Okay, Desmos, I'm trying to. Why won't it go right at 3? Usually this works so nicely, and it's just not today. Yeah, that's weird.
Wait, isn't it at -3?
Oh, yeah, that's probably why too. Okay. Ah, there we go. Cool. Yeah, so that's why I wasn't like trying to click there. Yeah, see, proof, no issue at 3. All right, but at -3, due to computer programming, the pixels are just filling in, all right, even on a TI or any type of computer, because it's, like I said, you can be microscopically close, and it wants to be that value, so pixels are just filling it in. But Desmos has this option, like if you at least click and drag, you can confirm there is a hole in the graph there. So literally a hole.
So when we are graphing this, you want us to like draw holes?
I'm not going to make you graph by hands, but if you did, yes. I just want you to identify them. And if you had to do it, you would draw like a hole. Yeah. All right. So I'll spare us. I was going to make us factor. I don't feel like factoring anymore. You're welcome. But we got that to do. All right. Where are my asymptotes on this graph? What are my vertical asymptotes? Y2. So if I sub in 2, I get not 0. I don't get 0. 2 is not a 0.
So it's 1 and -6, right?
1 and -6. You have 2 asymptotes, 2 vertical asymptotes, 1 and -6. The easy answer here is let's look at Desmos. The more interesting question is, before Desmos, what would you do? Meaning, is this graph going to go downwards or upwards here? Plug-in points. All right. Plug in points and find out. So let's look at values. I'll come back to -6 just the way I organize my table. I want to start at 1. I'm curious what's going on as we get close to 1 from the left. So again, the easy answer is Desmos. But without it, it's a good opportunity to just see something clever. So here's a number that's pretty close to 1 from the left. And while this might seem painstakingly hard, I'm not actually going to calculate number values. All I'm going to think about is if it's positive or negative. 0.99 plus 2. So what would this numerator become? Which is a positive number. So we'd have a positive number. We sub in 0.99 here. This factor would become negative. This factor would become 6.99, which is a positive number. See, I don't even care its value. I could say a positive plus 6 more is going to stay positive. Ooh, I can see because I'm really close here, that's going to make a negative. That's positive. So we have a positive divided by a negative times a positive. What's the output? There's my answer. As I'm really close to 1, the output has to be negative. We already know it's a asymptote, so it's got to be branching downwards. I'm feeling like it's going to branch upwards on the other side, but it doesn't matter what I feel. I should check it. Positive, positive, positive. Okay. That was much easier. And now we have evidence. We know it's an asymptote. If we trust it, it is. That's why I took the time to say, get really close, get close as you want to these numbers. But you're just going to be multiplying by 100 over 1,000, so they're going to get bigger and bigger and bigger. And now we're going to do a shortcut and say, okay, let's just determine the signs using kind of like a sign chart. Negative 6.01, that's just past negative 6. So technically we're coming in from the left. We're looking at it on the left side. Negative, negative, negative is a negative altogether. Negative 5.999, so an input like right here. Negative, negative, positive. So a negative, negative times positive, that's going to be negative, but a negative divided by a negative will be a positive. Now we know what the graph is doing without a graphing calculator. So notation-wise, as x approaches 1 from the left, that's what this means. The y coordinates are falling infinitely. As x approaches 1 from the right, that's this side, the y coordinates or the outputs are rising infinitely. As we approach negative 6 from the left, they're falling. As we approach negative 6 from the right, they're rising. Is that end behavior? No. End behavior is when you look at x goes to negative infinity to infinity. But it's the same notation. It's the same notation. That's really it, except for this last thing. If your rational function is exactly 1 more than your denominator. So just to review, bottom heavy goes to 0. Equal degree ratio of the coefficients. Top heavy, there's no horizontal asymptote. This is top heavy. There will not be a horizontal asymptote. But what we will see is called a slant asymptote. So it's not horizontal, it's going to be slanted, called linear. It's going to be a line. To find it, you divide. I'm going to use long division because we used synthetic earlier. So I'll just go with long, and I'll also say one other thing about that. So we would multiply by x. X times x is x squared minus 2x. Subtracting makes 4. Bring down your negative 3. You can stop right there. You don't actually have to complete the whole execution. Y equals x plus 4. Okay. But I'll explain why you can stop right there by finishing this problem, and then I'm not going to do it again. because that's how I like to teach math. Like, show you what I actually do, show you what you need to know how to do, but not just tell you this is it, but why this is it. So if we did finish this, it'd be 4x minus 8. And we'd subtract, and we'd get 5. So that would be our remainder over x plus, x minus 2. As x gets large, that's what end behavior is. I just said it. We know that. We know this right here. That's our reciprocal graph from 1 hour ago. That's been shifted over 2, but it still has a branch in quadrant 1. And in the long run there, what does this value become? 0. Because it's bottom heavy. This is a constant on top of a linear. This right here, in the long run, is going to become 0. You need more evidence? Plug in numbers. 5 divided by 10, 8, 5/8. 5 divided by 102 minus 2, 5 over 100, smaller. 1,000,002 minus 2, 5 divided by 1,000,000, really, really small. In the long run, that's going to 0. So what's left over? Stuff that looks like this. This is getting bigger, plus 4. This is going to behave like this line. So that's why I said we can stop right there. We don't need the remainder. Once you have your linear, this is called your slant asymptote. I'm not going to tinker with this thing, although I really want to. But it'd be cool to look at Desmos and literally see the line graph x plus 4, and that this curve approaches it. We won't, though. Find the slant asymptote. Trick question. There isn't one. Why is there not a slant asymptote? The numerator must be exactly 1 more than the denominator. If they're equal degrees, there's a horizontal asymptote at the ratio of their coefficients, but no oblique. Okay, I'm skipping the vertical part just for time's sake. What is our slant asymptote? The degree of the numerator is exactly 1 more than the degree of the denominator. So use long division. X squared times x gives us x cubed. Subtracting here makes 4x squared. Subtracting here makes negative 5x. Bring down the 6. And I'm done. Once you have your linear, you know you're done.
I think it's 8x squared. No.
Negative 2 minus negative 6. Very well could be, but x times x is x cubed. X times this is negative 6. And when you subtract, keep, change. So this is 6 minus 2. It should be 4. So it would be x plus 4. Again, what that is a slant asymptote. In the long run, it's not horizontal. It's not getting closer to 0. It's getting closer to a line.
Okay, so taking this one step further, if your numerator is 2 degrees more than the denominator, what happens?
You have a parabolic asymptote. Most people don't know that, and no one studies that. But
I guess it makes sense because then your line will then become square.
which is why I took the time when we did long division and said, what's your remainder? It's like, so for instance, if this was 4, and this is a quadratic, the remainder is going to be at most a quadratic, because you could have a quadratic left over, or a linear, or a constant. But to me, it just makes sense because of how division works, what your remainder is going to be. Let me rephrase that. Your remainder would be linear, but what would your quotient be? It would be quadratic. So in the long run, it's going to act like a parabola. If this was 5 greater, it would look like some 5th degree polynomial, which is just crazy, but it is true, because that's what it's doing in the long run. Your remainder is going to go over this, and in the long run, it's going to just go to 0. So it's whatever your quotient is. Yeah, but that's that. That's really our lesson. So the main points here were definitely know 1 over x graphs. 2 branches, 2 asymptotes, your center's HK. If you needed to sketch a graph, plug in a point. Be able to write the equation of a reciprocal function under transformations. And then the big takeaways here are vertical asymptotes, holds, horizontal asymptotes. Not 0 over 0, 0 over 0, and then top heavy. Nope, I said bottom heavy, equal degree, bottom heavy. That's horizontal end behavior. But if you're exactly 1 more, then you have end behavior that's approaching a line. I think everyone's ready for spring break. So I'm only going to do one of these because it's very procedural, as I said. And then I'll have a closing remark. Solving rational equations. It's not that fun. It's not that exciting. There's, again, no problem solving. As an example, this has nothing to do with graphs per se, all right? This is just solving a rational inequality. And there's a reason why we need this, but not something like, so you'll see in a few lessons. It's not that big of a deal though, all right? So I want to know what x values can I substitute in such that the left side will be greater than or equal to 3? And it seems like a harmless question. The way to attack this is make one side 0. Okay, that's easy. Two, build a common denominator so here's the denominator of x plus 2. This is a denominator of invisible 1. We can build a common denominator by putting them all over x plus 2. Since we have a common denominator, we can combine the two fractions. We'd have 4x plus 5 minus 3x minus 6. So not dragging this on forever. We'd have 4x minus 3x becomes x. 5 minus 6 becomes minus 1 is greater than or equal to 0. and what I showed you before becomes our tool. What did I show you before? You're going to choose an X value. We're not going to do any number crunching. We're just going to determine whether it's positive or negative, and then we'll know what this expression is. And if it's positive in the end, it's greater than or equal to 0. Now, what numbers should we substitute in? What are our zeros? -2, but 1 could also make a whole. All right, but let me just restate this, why this is important. When could this possibly be 0? At 1. So we would definitely want to test 1. We want to test near 2. Let me do one other thing, just to make a little more sense of this. So 1, -2. We actually want to test something here, here, and here. We're going to test 3 intervals. So I'll take -1. I'm sorry, I'll take -3, which is in that test interval. I'll take 0, which is in this interval. And I'll take 2, which is in this interval. And just say -3 minus 1, negative. -3 plus 2, negative. A negative divided by a negative is positive. And that's okay. I need it to be positive or equal to 0. I'll take 0. This becomes negative. This becomes positive. And this would be negative. So nothing in here works. If we take 2, you get positive. You get positive. You get positive. So we know the solutions to that inequality live from -infinity to 2, union 1 to infinity. Always put parentheses on infinity symbols, and you put square brackets if the number works. Does 2 work? I don't know. Guess what I'm going to do? Check it. 2. Oh, that is a -2, isn't it? Yep. I'm going to check it. Sub in -2, and it's a division by 0. So it needs to be not included. But if I test 1, you get 3 in the denominator, you get 1 minus 1 in the numerator. 0 over 3 makes 0, which does satisfy the inequality. This is your solution. So not the biggest thing in the world. Build a common denominator. Get one side equal to 0. Build a common denominator. It's pretty procedural. Choose numbers in between all the zeros. Do a quick sign chart, which is useful not just in determining asymptotes, but in stuff like this. And there's your solutions to that inequality. For the first time this semester, I'm done early. There is some homework, as I said now, for a few times. It will be due 2 weeks from today. So if you're taking some time off for till, like Sunday night or next week, when like the week we come back, just know when we come back on Tuesday, there'll be a new assignment, and it starts trigonometry. I know some of us came in a little bit later. So day 1, we're moving into trig. This unit of like polynomials and algebra stuff temporarily goes away. We'll be in trig for a little bit. That'll be the majority of exam 3, which is about a month away. Check the syllabus for the exact date on that. But this technically will be like the only non-trig stuff on exam 3. If you didn't get exam 2, see me before you leave. Otherwise, enjoy your time away from school. get some much needed rest, I'm sure. Abigail,